Hello Gate Warriors, welcome back to ShortGATE. Today we are branching out further into the worlds of trees, exploring the efficient world of binary search trees. These trees are essential not just for theory but for problem solving, algorithms, and practical applications. Ready to dig deep into the structures? Let's go. Now see, what is binary search tree? A binary search tree is a type of binary tree with a special property. The left child of the node contains a value less than the node's value. The right child contains a value greater than the node's value. This structure allows for efficient searching, insertion, and deletion operations. It performs the backbone for many searching and sorting algorithms. Now, let's see the key properties of binary search trees. Left subtree, root, right subtree. This ordering makes searching is efficient. No duplicate nodes. Each value must be unique to maintain the BST property. Each subtree is itself a binary search tree, following the same rules. You can traverse BST in various ways to extract sorted data or perform operations. Why we use BST? BST are widely used because of their efficiency in the following areas: fast searching, efficient insertion and deletion, data organization, ideal for real-world applications like databases and file system, flexible traversal. You can access data in any order you need. Now see the key operations of BST. There are three main operations we perform in binary search tree: insertion, deletion, and searching. In insertion, start at the root, compare the new value with the current node, and recursively insert it in the left or right subtree depending on its value. For deletion, this is strictly tricky, as you may need to delete a node with 0 or 1 or 2 children. You will learn about replacing nodes and maintaining the BST property. For searching, it is similar as insertion. Traverse the tree starting from the root, going left or right depending on whether the search values is smaller or greater than the current node. These operations work efficiently when the tree remains balanced. Let's walk through an example. Insert the following values into an empty BST. Starting with 20, we will compare and place each values to maintain the BST property, such as 20 is the root and next 10 is less than 20. For this reason, 10 is placed at left in the root. You can see how each value fits into the correct position based on comparison. This structure allows for efficient searching. Now see the time complexity. The efficiency of binary search tree depends on whether it's balanced or unbalanced. For best case, time complexity is order of log n for searching, insertion, and deletion in a balanced tree. For average case, order of log n for most random data inputs. And for worst case, mean unbalanced tree, order of n. Whether the tree becomes skewed like a linked list. Now that we have covered binary search trees, it's time to practice and implement them to solidify your understanding. If you found this video helpful, here's how you can keep learning. Like the video if it helped you understand BST. Subscribe to ShortGATE for more gate preparation content. Comment below with any topics or questions you would like me to cover next. In the next video, we will explore self-balancing trees like AVL trees, which ensure that your BST stays efficient even in the worst case. Keep learning and together we will crack the gate. Thanks for watching. As we keep growing our knowledge or data and algorithms, don't forget practice is the key to mastering concepts like binary search trees. Stay curious, keep coding, and remember, success in GATE is just a step away. If you keep learning smart, until next time, happy studying.